This video is part of an online undergraduate course on complex analysis and will be about the famous residue calculus. So the main theorem of the residue calculus is as follows. Suppose f is holomorphic in some region and we want to work out the integral of f around a curve C. Well, by Cauchy's theorem, we know the answer to that. The integral is just 0. But now suppose f is holomorphic except at a few points. So there might be 3 points in here where f isn't holomorphic. Well, then we want to know what is the integral around this curve, and the residue theorem says it's 2 pi I times the sum of the residues at these points. Okay, so what's the residue at a point? The residue at a point is 1 over 2 pi I times the integral around c dash of f of z dz, where c prime is just a little circle around this point. So if this point is P, then what you do is c prime is just a little curve around c prime. And again, by Cauchy's theorem, it doesn't depend on which little curve around the point you choose, as long as it's sufficiently close. And the proof of this theorem is almost trivial, from at least if you assume Cauchy's theorem. What we're doing is we're trying to say the integral around C is equal to the sum of the integrals around these 3 points where the curve is not holomorphic. And for that we just look at the following contour. We sort of put a couple of lines there and a couple of lines there and a couple of lines there, and we kind of go around like this, and then we go round here. So we do this red contour, and you see the red contour is just the integral around the big curve C minus the integral around all these little curves, except for these double lines here, and we notice that the integrals over all these double lines cancel out. So the integrals over all these two cancel, because if you look very carefully, you notice that in one of these lines we're going in that direction, the other line we're going that direction, and these two lines are actually the same, only I've drawn them slightly apart, so you can see there are really two lines there. So that shows we can work out an integral like this in terms of a sum of the residue. So the next problem is, what is the residue? So what is the residue of a function f of z dz at a point P? Well, what we do is we expand f as a Laurent series. So a Laurent series is like a power series, only you allow a few negative coefficients. So we have an a minus 1 z minus p minus 1 plus a naught plus a1 z minus p, and so on. So this bit is just a power series around z at p, and here we've got a few extra terms that aren't quite holomorphic at p. And then the residue of f of z dz at p is just a minus 1. You take the coefficient of z minus p to the minus 1. And the proof of this is very easily. Let's just take p equals 0 to make notation simpler, and then you recall the integral around z to the n dz is equal to 2 pi I for n equals minus 1, and 0 for n not equal to minus 1. Here's c is just a little curve around 0, of course. By the way, strictly speaking, we should only talk about the residue of a one form, which is a function times dz. Now, everybody is very sloppy about this and just talks about the residue of the function z rather than the one form f of z times dz. So the reason for that is that if we've got a 1 form, then the residue of f of z dz is invariant under a change of variables. So if we put y equals b1z plus b2z squared and so on, then the residue of this is equal to the residue of f of y dy at the corresponding point. Whereas if we don't put in the d there, then the residue might actually change if you change variable. However, most of the time we're not really changing variables very much, and it's a bit annoying to keep writing down this dz all the time, so we just sloppy and talk about the residue of a function at a point. So now let's do some examples of how to use the residue calculus. There are two ways of doing it. First of all, we can convert an integral into a sum, because if we've got an integral and it happens to be a contour integral, then it's just a sum of residues. The second thing we can do, which is slightly less obvious, is we can convert a sum into an integral. So if we want to evaluate a sum, then we can write it, if we're clever, we might be able to write it as a sum of residues, and then you might be able to carry out the integral around those residues. We'll see some examples of that this next lecture, and for this lecture we'll give some examples of evaluating an integral. So let's start off with an easy example, a sort of warming up exercise. Let's just do the integral from minus infinity to infinity of 1 over 1 plus z squared dz. Now, of course, you all know how to do this from introductory calculus. The indefinite integral of 1 over 1 plus z squared is just the arctan of z. So you take the arctan of z from infinity to minus infinity, and this is just pi over 2 minus pi over 2, which is pi. And in fact, you can work out the integral from anything to anything else in the same way. So this doesn't really demonstrate the full power of the residue calculus. It's just to get us started. Well, so let's look at what we're integrating. We're integrating this function 1 over 1 plus c squared, and we're integrating it along this line here. Well, there's a bit of a problem because we can't apply Cauchy's theorem to this, because Cauchy's theorem only applies if we're integrating over a loop. So what we do is we change this a bit. What I'm going to do is I'm going to integrate along here and then integrate over a semicircle. So here's the point r and here's the point minus r. And you notice that as r tends to infinity, the integral along this straight line here tends to the integral we want. Well, what about the integral over the curved line? So what about the curved bit? Well, the integral over the curved bit, the integral of the absolute value of the integral over the curved bit is less than or equal to the length of this curve, which is 2 pi r, times the maximum of the function on this curve. Now, on this curve, the function is about 1 over z squared, if we don't worry about that too much. So that's going to be at most, say, 2 over r squared, because z will have absolute value r. And this is equal to, say, 4 pi over r, and this tends to 0 as r tends to infinity. So we can ignore the integral over the curved bit because we're going to take a limit as r tends to infinity. So we've managed to turn our integral from minus infinity to infinity into an integral over this, this piece here. Now we can apply the residue theorem. So we need to know, what are the points where this is not holomorphic? Well, obviously there's z equals I and z equals minus I. And we don't care what happens at minus I because that's outside the contour. So by the residue theorem, the integral over the red bit is just the residue at I. So we have the integral from minus infinity to infinity of 1 over 1 plus c squared dz is equal to the integral over the red thing, at least if r is big enough, which is equal to 2 pi I times the residue at z equals I. So now we need to figure out what is the residue at z equals I. And what we're trying to figure out is the residue of dz over 1 plus z squared. And it's useful to write this as dz over z minus I times z plus I. And now we notice the integral of dz over z minus p times g of z. If the residue of this at z equals p is just g of p, provided g of z is holomorphic at z equals p. So we apply this here. Well, we ignore this z minus I because that's the z minus p there. And what we want is just the value of this at z equals I. So the residue is equal to 1 over 2I. So you see it's actually quite easy to calculate the residue. So this becomes 2 pi I times 1 over 2I, which is equal to pi, which is the answer we got before. Well, if that was all you could do with the residue calculus, it would be really unimpressive, since it's just a rather fancy way of doing something we can do very easily anyway. So let's try a slightly different example. This time I'm going to ask for the integral from minus infinity to infinity of cosine of x over 1 plus x squared dx. And now if you try and use elementary calculus on this, you get stuck, because we want the antiderivative of cosine x over 1 plus x squared, and this is equal to, well, I don't know. There's no easy way to write the antiderivative of this function in any easy function. The easiest thing to do is to just call it the antiderivative of this. So when you go to introductory calculus courses, it's kind of all a bit of a fake. You're taught all these clever ways of integration by parts and by substitution, and shown how to do lots of integrals, and it's all totally misleading, because most integrals you just can't do like that, and this is one of the integrals you just can't do in elementary terms. So let's try and copy the contour integration method. So what we do is, just as before, we've got the integral from minus infinity to infinity, and now let's try to write it as an integral over a big semicircle. And this looks quite promising at first sight, because again we're going to have a residue at I, and maybe we can turn this integral over a residue. So the first thing we ask is, how big is cosine x over 1 plus x squared on this semicircle? And you think, well, that's easy, because cosine x is bounded by 1, and 1 plus x squared is very small, just like in the previous video, so this is going to be 0. And that's completely wrong, because cosine x is huge when x has large imaginary parts. You remember the idea that cosine x is bounded is just completely wrong for complex analysis. And we just seem to be stuck. The integral over there is huge, and it's no point trying to integrate down there because it's equally huge. Well, there's a very neat trick for dealing with this, which is that instead of cosine x, we look at the integral of minus infinity to infinity of e to the ix over 1 plus x squared dx. And this is the integral from minus infinity to infinity of cosine x over 1 plus x squared dx plus I times the integral from minus infinity to infinity of sine of x over 1 plus x squared dx. And now we can see that if we can do this integral, then its real part is this and its imaginary part is this. So this is just the real part, and this bit here is the imaginary part. So if we work out this integral, we can figure out both of these integrals. Actually, you may have noticed that in fact this integral here is 0 because we're integrating an odd function. So in this particular case, this integral is actually equal to that integral, but in general we would get two separate real integrals. Well, what's the point of that? Well, cosine x we saw was huge, so we couldn't show that this integral here was 0, but e to the ix is really tiny on this red path because it's sort of looks roughly like e to the minus x, where x is a large real number. Notice, by the way, that although it's tiny here, it would be absolutely huge down here. So we have to be careful to go in the positive half plane, not the negative half plane, if we're using e to the ix. Actually, we don't really need e to the ix to be tiny. We just need to notice that e to the ix is absolute value at most 1. So the integral over the semicircle tends to 0, just as in the previous one, and we find the integral from minus infinity to infinity of e to the ix over 1 plus x squared dx is just equal to 2 pi I times the residue. So now we've got to work out what is the residue at the one point where it's not holomorphic. Well, there are 2 points where it's not holomorphic, but we don't care about that one because it's not inside this contour. So we see the integral from minus infinity to infinity of cosine x over 1 plus x squared dx is 2 pi I times the residue of e to the ix dx over 1 plus x squared at x equals I. And now we just have to work out this residue, and we can do that as before, because we can write this as x minus I, 1 over x minus I, and let's put the dx there because this is the bit we don't care about, times e to the ix over x plus I. And now we've got the dx over x minus I, so the residue is just the value at x equals I, where the I is just this bit here. And that's easy. Well, this is just e to the minus 1 over 2I. So this integral here becomes 2 pi I times e to the minus 1 over 2I, which is equal to pi over e. Well, having done that, we've done the integral from minus infinity to infinity. Well, why don't we try the integral from, say, 0 to x of cosine x over 1 plus x squared dx. And if we try doing this by contour integral, we just get completely stuck because we need to integrate from 0 to x. And if we try making that into a closed contour by doing something, well, we get this complicated closed contour, and we may be able to say the sum of this integral and this integral is some sort of sum of residues. That's no problem. But the trouble is we wouldn't be able to say anything very much about this closed contour because we can't move it to somewhere where it becomes 0 because it's kind of fixed here. So contour integration is not very much use for doing integrals between arbitrary points. We can only do integrals between very special points. Often infinity and minus infinity are special points, and places where the integrand does something funny are often also special points. So you might think, well, that means contour integration is sort of useless. We can only work out a few very special sorts of integrals. Well, that's sort of true. But on the other hand, it turns out the special integrals you can do with the calculus of residues are very often the integrals you actually want to know. So for the final example in this lecture, I will do a slightly more complicated version of the previous example, which introduces 2 extra complications. So now I'm going to do the integral from minus infinity to infinity of sine of x over x dx. And let's try doing this by a contour integral. Well, as before, if we try doing it, converting it into we can convert it into a semicircle, but the trouble is, as we saw, sine of x is too big here. Well, we know how to fix that. We just do the integral from minus infinity to infinity of e to the ix over x dx, which is equal to the integral from minus infinity to infinity of cosine x over x dx plus I times the integral from minus infinity to infinity of sine of x over x dx. Right? Well, no, there's a problem with this, because what happens to this at x equals 0? It becomes infinite. So this integral is a bit fishy. I mean, it's you have to be really rather careful when dealing with it, because the integral of the absolute value of this is actually infinite. So how do we fix that? Well, the other problem we notice is that this thing has no points where it's non-holomorphic except at x equals 0. So this is holomorphic except at x equals 0. So what can we do to fix these two problems? Well, what we do is we look at the following contour. What we do is we integrate round a big semicircle, and we also integrate round a little semicircle. And you notice this little semicircle avoids this problem here. So let's stop and think what we've got. Well, the integral along these two straight bits tends to the integral from minus infinity to infinity of sine of x over x dx, or at least up to factors of I guess it actually tends to I times that. At least its imaginary part tends to. Let's not worry about the real part for the moment. So what we've got to do is we want to show that this circular part tends to 0. So let's say that this circle is radius big R and this circle is radius little r. And the other thing we want to know is, what does this little circle tend to as r tends to 0? So we've now got two semicircular contours to estimate. And let's do the big one first and then do the little one. So here we're trying to estimate the integral round this semicircle here of e to the I x over x. If we just integrate 1 over x dx over this semicircle, we can bound that by saying it's less than or equal to the length of the semicircle, which is pi r, times the absolute value, maximum of the absolute value of 1 over x, which is 1 over r, which is equal to pi, and this does not tend to 0. So if we just say e to the ix is less than or equal to 1, we don't get, our estimate isn't quite good enough. On the other hand, if we try and bound it by e to the ix, so the integral of e to the ix dx, well, this doesn't tend to 0 either, because e to the ix is about 1 here. Or the absolute value of e to the ix is about 1. So we seem to have a problem. E to the ix isn't quite small enough to show the integral tends to 0, and 1 over x isn't quite small. But if we combine these, we can show the integral does tend to 0, because e to the ix is sort of very small here, and in the remaining bits, in these bits here, 1 over x is fairly small. So if we sort of put these two together, we can show the integral tends to 0. So what we do is we pick some number m, so e to the ix has absolute value less than epsilon whenever the imaginary part of x is greater than m. So we're just choosing some number m here. And then we the integral over the bit above m, above mz equals m, so the integral over this bit here is going to be at most epsilon times this bit here, which is pi, which tends to 0. Sorry, let's not take it to tend to 0 here. And now we have the integral over the 2 bits below m. Well, this time it's bounded by approximately 2m times 1 over r, because the absolute value of x is about 1 over r, and the length of these paths is about 2m. Well, it's slightly bigger than 2m, but who cares? So it's approximately less than that. And this now tends to 0 as r tends to infinity. So we can make the integral less than or equal. What we can do is we pick epsilon as small as we like, and then the integral over the bit above m will always be at most epsilon times pi, and the integral over this bit, we can make it at most, say, epsilon by taking r to be as big as possible. So by taking r sufficiently large, the integral is going to be less than, say, epsilon pi plus epsilon, which tends to 0. So the point is, this is a slightly messy estimate that the integral over a contour tends to 0. And what you do is you split up the contour into 2 pieces and estimate the size over each of these pieces. Anyway, the conclusion is the integral over the big semicircle tends to 0, and we can ignore it. Now we have to deal with the integral over the small semicircle of radius r, of radius little r. So we want the integral over this of e to the I x over x dx as r tends to 0. Unfortunately, this tends to a limit. First of all, we notice the integral over c of e to the I x over x dx, where c is a circle going all the way round the origin, is just equal to 2 pi I times 1, where this is the residue of e to the ix over x dx. So what's the integral over this bit here? Well, the integral over, let's call this contour d, the integral over d of e to the ix over x dx is now equal to minus a half times 2 pi I times 1. Why minus a half? Because we go minus a half times around 0. Sorry, it's not equal to that. It tends to that as r tends to 0. So you see we're going halfway round this contour, but we're going in a clockwise direction, which counts as being negative. So we're really doing minus a half anti-clockwise resolutions. And I'll explain why you get minus a half there in the next sheet. But meanwhile, this tells us what the integral here is. So the integral of from minus infinity to infinity of sine of x over x dx is just going to be times I is just going to be this thing here, which is just pi. So we've worked out our integral. All I have to do is explain why we get a minus a half there, and then we're done. So what we're doing is, if we integrate a fraction alpha around 0, so let's integrate around this contour c here of a minus 1 over z to the over z plus a naught plus a1z and so on dz. Well, we can calculate this by working out this bit explicitly. So the integral of this bit just turns out to be I alpha times a minus 1. And we can work out that by doing the integral explicitly. We did it for alpha equals 2 pi, and the integral for any alpha is the same. On the other hand, this bit here just tends to 0 because this is bounded. This is a bounded function, and the length of the contour c tends to 0. So as this radius r tends to 0, we see the limit of this is just alpha times that. So if we integrate a fraction better not call it A of 2 pi, we get A times the residue. This is assuming that we only get factors of z to the minus 1 in our function. If we have extra terms with a minus 2 over z squared, then this rule doesn't hold. Next lecture we're going to show a different application of the residue calculus in order to work out sums, and in particular we're going to show Euler's result that the sum of the reciprocals of all the squares is pi squared over 6.